Welcome, ladies and gentlemen, to your second video in the series on physics. Today we're going to be talking about three things. We're going to be talking about the scientific method, we're going to be talking about the SI base units, and we're going to be talking about prefixes. Now, if you don't have a piece of paper and a pencil right now, I want you to go get one. Pause this video, go get a pencil, and your notes. Print out the note. If you have the printed out notes, get those. If not, do it the old-fashioned way and just write on a blank piece of paper. Go ahead. I'll wait. Good, you're back. Okay. So, let's start with the scientific method. The scientific method is a way for us as scientists to answer the questions of the universe. Like, the universe poses many questions that we don't know the answer to. So this is a method for us to find the answer. And I'll give you a quick example. Remember that 2, 4, 8 that we talked about yesterday? The question was, what's the pattern? So you construct a hypothesis. Oh, maybe 4, well, what was 16, 32, 64. You have a hypothesis. You run it through the experiment. The guy he would tell you, yes, the experiment was put forth these answers, and he tells you, does it work, does it not work? Do your results align? And if they don't, you have to go back and reconstruct your hypothesis. If they do, you can say that my hypothesis is correct. So this is kind of an abbreviated method. So the most important part of the scientific method is asking a question. We really don't know how the universe works. We probably understand 30% of it. That's our best guess. But humans right now understand 30% of really truly what's going on around us. We don't know. Do some research. Work your way out to the sphere of understanding. Like, what do we currently know? What's currently being done with this question? Make an educated guess, a hypothesis. Test it. Make sure your experiment is working. Is it calibrated? Is it getting interference with something else? And then the question is, does my results, do they agree with my hypothesis? If they agree, then you're good. You communicate your results to the world. Science is about sharing. If they don't agree, then something is going wrong. My experimental data isn't jiving with what I thought. So what that means is either 1, my experiment is set up wrong, or 2, my thinking is wrong. So you check both of those. Check to make sure your experiment works. Maybe it doesn't. So I want to talk to you a little bit about the difference between a hypothesis and a theory and a law. We've heard those words before, and a friend of mine made a really interesting rap concerning these, and I wanted to show it to you right now.
No skills, research and entertainment. Theory versus hypothesis.
You got the theory and the hypothesis. Have you ever wondered what the difference is? You got the theory and the hypothesis, but have you ever wondered what the difference is? Go!
You hear it all the time. People tell you about their theories, but what they mean to say is that they have hypotheses. Hypotheses are the ideas that can be tested. You do it all the time. They're called educated guesses. Hypotheses are based on observations, and testing is done for further evaluation. Evidence is gathered to disprove or support it. Theories contain hypotheses that support them. Hypotheses are the ideas that people are working on, and theories are the explanations of phenomenons. Theories are precise and theories define. Theories contain contributions from remarkable minds.
The study of physics is pretty amazing. Explains universal mathematical equations, but luckily you don't need a PhD to understand what string hypothesis means. That sounds weird, doesn't it?
The theory of evolution explains life on our planet. The theory of relativity explains motion is standing. And some of these theories are extremely old, but that doesn't mean that they're set in stone, because theories are modifiable and rejectable. If and only if new evidence is acceptable. Science is cool and it's always changing. The greatest tool ready for new information. I know it sounds cool, but now that we know what the difference is, instead of a theory, what you got is a hypothesis. I know it sounds cool, but now we know what the difference is. Instead of a theory, what you got is a hypothesis. Dark matter, theory or hypothesis. Dark energy, theory or hypothesis. String theory, theory or hypothesis.
What do you think?
I'll give you the hook so that you can think of this.
The theory and the hypothesis.
Have you ever wondered what the difference is? You got the theory and the hypothesis, but have you ever wondered what the difference is? Go! Dark matter is a hypothesis, and that's because we don't have enough evidence.
Yeah.
Dark energy is a hypothesis,
Yeah.
and that's because we don't have enough evidence.
Yeah.
String theory is pretty tricky.
That's right.
Math checks out, but we don't have enough evidence.
Yeah.
Relativity, it's a theory, y'all.
Y'all.
It concisely explains a phenomenon.
Oh.
And gravity, it's a theory, y'all. It concisely explains a phenomenon. But it's also a law. Uh-oh, looks like we have to write another song.
So there you go. The difference between theories, hypothesis, and laws. Hypothesis is the guess, the initial guess. Once you run the hypothesis through enough experiments, then it can become a theory. And there's actually there's numbers to how many experiments, like how statistically significant is this hypothesis that will elevate it to the level of a theory. And then theories become laws. Exactly, there's the same number of, there's a quantitative number that elevate theories into law. And it's funny how he mentioned the law of gravity, because we have no idea how gravity works. No clue whatsoever. I want to introduce you to another one of my friends. His name is Adam Savage. You might know Mr. Adam Savage from Mythbusters. He was asked to speak at TED, and it talks about questions. And I wanted to share this with you because it's really neat with the scientific method here.
One of the funny things about owning a brain is that you have no control over the things that it gathers and holds on to, the facts and the stories. And as you get older, it only gets worse. Things stick around for years sometimes before you understand why you're interested in them, before you understand their import to you. Here's 3 of mine. When Richard Feynman was a young boy in Queens, he went for a walk with his dad and his wagon and a ball. And he noticed that when he pulled the wagon, the ball went to the back of the wagon. And he asked his dad, why does the ball go to the back of the wagon? And his dad said, that's inertia. He said, what's inertia? And his dad said, inertia is the name that scientists give to the phenomenon of the ball going to the back of the wagon. But in truth, nobody really knows. Feynman went on to earn degrees at MIT, Princeton. He solved the Challenger disaster. He ended up winning the Nobel Prize in physics for his Feynman diagrams describing the movement of subatomic particles. And he credits that conversation with his father as giving him a sense that the simplest questions could carry you out to the edge of human knowledge, and that's where he wanted to play. And play he did. Now, Eratosthenes was the 3rd librarian at the Great Library at Alexandria.
This is a great story.
And
I
he
love
made
this
many contributions to science. But the one he is most remembered for began in a letter that he received as the librarian from the town of Swenet, which was south of Alexandria. The letter included this fact that stuck in Eratosthenes' mind. And the fact was that the writer said at noon, on the solstice, when he looked down this deep well, he could see his reflection at the bottom, and he could also see that his head was blocking the sun. Now, I should tell you, the idea that Christopher Columbus discovered that the world is spherical is total bull. It's not true at all. In fact, everyone who was educated understood that the world was spherical since Aristotle's time, and Aristotle had proved it with a simple observation. He noticed that every time you saw the Earth's shadow on the moon, it was circular. And the only shape that constantly creates a circular shadow is a sphere, QED. The Earth is round. But nobody knew how big it was until Eratosthenes got this letter with this fact. So he understood that the sun was directly above the city of Swenet, because looking down a well, it was a straight line all the way down the well, right past the guy's head, up to the sun. Eratosthenes knew another fact. He knew that a stick stuck in the ground in Alexandria at the same time and the same day at noon, the sun's zenith, on the solstice, the sun cast a shadow that showed it was 7.2 degrees off axis. Now, if you know the circumference of a circle, and you have 2 points on it, all you need to know is the distance between those 2 points, and you can extrapolate the circumference. 360 degrees divided by 7.2 equals 50. I know, it's a little bit of a round number, and it makes me suspicious of this story too, but it's a good story, so we'll continue with it. He needed to know the distance between Swenet and Alexandria, which is good, because Eratosthenes was good at geography. In fact, he invented the word geography. The road between Swenet and Alexandria was a road of commerce, and commerce needed to know how long it took to get there. It needed to know the exact distance, so he knew very precisely that the distance between the two cities was 500 miles. Multiply that times 50, you get 25,000, which is within 1% of the actual diameter of the Earth.
Isn't that awesome?
He did this 2,200 years ago. Now, we live in an age where multi-billion-dollar pieces of machinery are looking for the Higgs boson. We're discovering particles that may travel faster than the speed of light. And all of these discoveries are made possible by technology that's been developed in the last few decades. But for most of human history, we had to discover these things using our eyes and our ears and our minds. Armand Fizeau was an experimental physicist in Paris. His specialty was actually refining and confirming other people's results. And this might sound like a bit of an also-ran, but in fact this is the soul of science, because there's no such thing as a fact that cannot be independently corroborated. And he was familiar with Galileo's experiments in trying to determine whether or not light had a speed. So Galileo had worked out this really wonderful experiment where he and his assistant had a lamp. Each one was holding a lamp, and Galileo would open his lamp and his assistant would open his lamp. And they got the timing down really good. They just knew their timing. And then they stood at two hilltops 2 miles distant. And they did the same thing on the assumption from Galileo that if light had a discernible speed, he'd notice a delay in the light coming back from his assistant's lamp. But light was too fast for Galileo. He was off by several orders of magnitude when he assumed that light was roughly 10 times as fast as the speed of sound. Fizeau was aware of this experiment. He lived in Paris, and he set up 2 experimental stations, roughly 5.5 miles distant in Paris. And he solved this problem of Galileo's, and he did it with a really relatively trivial piece of equipment.
This is really cool. He finds the speed of
He
light.
did it with one of these. I'm going to put away the clicker for a second because I want to engage your brains in this. Now, this is a toothed wheel. It's got a bunch of notches, and it's got a bunch of teeth. This was Fizeau's solution to sending discrete pulses of light. He put a beam behind one of these notches. If I point a beam through this notch at a mirror 5 miles away, that beam is bouncing off the mirror and coming back to me through this notch. But something interesting happens. As he spins the wheel faster, he notices that it seems like a door is starting to close on the light beam that's coming back to his eye. Why is that? It's because the pulse of light, it's not coming back through the same notch. It's actually hitting a tooth. And he spins the wheel fast enough, and he fully occludes the light. And then, based on the distance between the 2 stations and the speed of his wheel and the number of notches in the wheel, he calculates the speed of light to within 2% of its actual value. And he does this in 1849. This is what really gets me going about science. Whenever I'm having trouble understanding a concept, I go back and I research the people that discovered that concept. I look at the story of how they came to understand it. And what happens when you look at what the discoverers were thinking about when they made their discoveries is you understand that they are not so different from us. We are all bags of meat and water. We all start with the same tools. I love the idea that different branches of science are called fields of study. Most people think of science as a closed black box, and in fact, it is an open field, and we are all explorers. The people that made these discoveries just thought a little bit harder about what they were looking at, and they were a little bit more curious. And their curiosity changed the way people thought about the world, and thus it changed the world. They changed the world, and so can you.
And they stick with their problems. They don't give up easily. They don't give up easily. Let's talk about SI base units. These are the units that which we define everything in the universe. There's 7 of them. The first one is length, and our SI base unit for length is the meter. In the English system, we use feet, but in the SI base unit, we're going to use meter. I can actually move this over here. Its symbol is M, and its base unit is meter. The SI base unit for mass is a kilogram. Dang it.
Attention students, just a reminder, there will be no carrying food or deliveries to the commons today, only school food is being to the commons today.
kg.
And please keep up
The
your
SI base unit for time is the second, abbreviated with the letter S. Temperature is going to be Celsius. Amount of a substance is a mole. You might remember that from chemistry class. Electric current is the amp. And luminous intensity is candela. Now, just to give you an idea, like speed, for instance. We all know speed. Speed is not a SI base unit. Like, you don't see speed written over here. But what you do know is that speed is like feet per second. It's distance per time, so it's meters per second. That's another way to write speed. So we can combine these things in a lot of different ways. If you know anything about torque, that's like foot-pounds, distance and force, and then force isn't up here, so what's force made out of? Here's your assignment for tomorrow. I want you to jump on my website, and when you jump over the website, there's this National Physical Laboratory. What I want you to do is you have to pick, there's a video, pick a number between 1 and 7, because there's a video for each of the 7 SI base units. The meter. This explains the history of the meter. Where did the meter come from? How do we measure? What is a meter? How do we define it? Excuse me, today. I want you to do that. Take a look at it, and I want you to be able to talk about it. I'm going to have you get in groups of 7 and just share with each other, what is a mole? How do we know what a mole is? Like, how do we define a mole? It's very interesting. So it's just right here, this NPL National Physical Laboratory. Watch another one of those videos. The last part I want to talk about today is prefixes. Prefixes. These are things that go in front of our measurements to delineate how large. Like the prefix F stands for femto. The P stands for pico. N stands for nano. This thing is the Greek letter mu, M-U, and it stands for micro. M is milli. C is centi. D is deci. K is kilo. Here is a divider. M is mega. G is giga. And T is tera. Now, you'll see you have to have these memorized for the test. You have to know how to do and what each of these means. Right here, these you see a lot of times in computers. A kilobyte, a megabyte, a gigabyte. Maybe you've heard of a terabyte if you're into computers. But you'll notice that each of these goes up by a factor of 3 each time. So a gigabyte is 1,000 times bigger than a megabyte. A terabyte is 1,000 times bigger than a gigabyte. So they're going up by a factor of 3. Milli, centi, deci, these are ones you probably are familiar with. Down here, these ones maybe not so much. Here's how I remember this. Micro sounds like million. A micrometer, it's 1/1,000,000th, 10 to the negative 6th. Nano sounds like 9. Ten to the negative 9th. Pico, Pikachu, if you ever were into, he's 12 years old. So it's 10 to the 12th. Pikachu, he's 12 years old. And femto sounds like 15. These are what are called mnemonic devices, ways how we can remember this. Femto sounds like 15. Pikachu, he's 12. Nano, 9. Micro sounds like million. Mega also sounds like million. They start with the letters M. Milli, 1/1000th. So you have to have all of these memorized for your test because we're going to be using these throughout the entire year, and you have to know how to handle these. So here's part 2. I'm sorry it was 20 minutes. I wish it would have been a little bit shorter. The scientific method, SI base units, and prefixes. Remember, go on the website, look up any one of those, and be ready to talk about it tomorrow.